Hi, good morning. Yeah, there was a little the problem on the mic. That's why I got a little down. Hopefully this time it should work. Okay. Hopefully yesterday quite a few students also attend Yuri Leskovic's talk. How many people attended? That will get a very good crowd. Yeah, you probably see we actually learned or lectured on some of his papers. Remember, we have this, when the time grows, when the time goes along, whether the network will shrink or will grow. Okay, I actually give one question in the midterm exam. I hope you all know what I intend is his paper. That means when the time grows, okay, along with the time when the network grows, actually the diameter is shrinking, right? I hope you all get it right. Okay? It should be a reasonable, good answer because he invented this, densification law. Once it grows, the number of edges actually grow superlinearly comparing to the number of nodes. That's why I get more connections. That's why you bring the diameter down, right? And we also have his forest fire model. Of course, in that question, I do not even ask you to touch the forest fire model, just to say, at least you should know the densification law. You get the edge grows more than the nodes. Okay. Hopefully you all answered right. Okay. That's him. You actually saw him yesterday. He gave a pretty interesting talk on, the cases on whether you want to bear the suspect or you want to, put the suspect in the jail. Okay. I think it's a pretty interesting application. You can see data mining, simple data mining method, just like a decision tree, actually can do quite a lot of good. Now we will continue our discussion on the text mining part. He was also got a little briefing on our phrase mining and typing. He got very impressed. He actually told the student there will be lots of applications. The student feel very proud of it because they actually just give the briefing. He fully understands what's going on and they give lots of very interesting comments. Okay. So we will continue, and then today we will have one student presentation. I give 15 minutes because that's a student requested. So we will lecture on 60 minutes, then we will finish at 10:30, then we get 15 minutes briefing. The only thing need to be changed is today's office hour, okay? Today's office hour, I'll change it to 1:30. The reason is I have to send Yuri Leskovic to the airport. Right after class, I have to go to his hotel, get an early lunch, then send him to the airport. So I have to, excuse for the office hour. We move it to 1:30. If you cannot make 1:30, you can look at my calendar. I think at 2:30 will also be available. Okay, that means 2:30 to 3:30. If you want to meet me, that's also fine. Okay. Feel free. You try to find me, discuss your project. You are more than welcome. Okay. Now let's get a little review on what we learned about the top mine. Okay. The top mine general philosophy is we based on large corpus. Okay. Then we have many sentences. Then you look at the occurrences of those words and see whether their occurrences together is more than expected or much more than expected based on their individual occurrence frequency. That means if the support occurs so frequent, vector occurs so frequent, but support vector getting together is much more than they just independently, you time them together on the probability. Okay, so that's a case. You will say they form a phrase, potential phrase candidate. Of course, you need to use, like we call segmentation. That means you go back to the concrete documents to see whether it's support vector contribute or support vector machine contributes. If the support vector machine contributes to the whole thing, then the support vector itself, their true frequency will go down, okay? Because for this particular case, it is support vector machine got the whole credit instead of support vector or vector machine got the credit, okay? Based on these raw frequency and true frequency computation, you will get the real frequency, you will get the real, probability, which one is a good phrase, okay? And not only you use significance score, you can use other things as well. Many other measures you can do almost as good, okay? Then if you want to do topic modeling, you can first get a phrase. Then you do modified LDA. Actually, today the student is going to give you a more detailed introduction on the LDA, which is very good, okay? Because I do not give you a detailed introduction. I only say what's the modification. The modification actually is for those words, once they form phrases, you think they form additional links. You will make them tighter in your derivation or in your generative model. So then you generate better quality topics, okay? So I show you here, for example, for DBLP, you probably can see you can get, for example, this one is programming languages, source code, object-oriented, type system, data structure, program execution. This is obviously software engineering, in computer science. You clearly see automatically you generate high-quality phrases and also high-quality topics. So that helps people to generate meaningful topics for topic modeling as well. Okay. And this one is for the Associated Press News in 1989. It also generates some, there are many, many topics. Actually, the total number of topics is hundreds. Okay? But if you look at each topic, you still see they are very meaningful. Very meaningful not only on the single words, but also meaningful on the phrases. Okay? This one is on the year preview. You probably can see, just give you a simple example. You look at this topic 5. You see the phrases, you get Mexican food, chips and salsa, food was good, hot dog, rice and beans. If you ever, tried Mexican food, those are very typical Mexican food menu. Of course, like I said, there will be something like food was good, which actually is a sentence instead of a phrase. But for phrase mining, because you do not do any natural language component, there's no part of speech tagging, there's no parsing. That's the reason you generate short sentences as phrases. Okay, but on the other hand, you add a little post-processing. For example, you can do some parsing or some part of speech tagging. You will be able to grab those out. Then you can get even better quality, right? So that's about top mine. Okay. And for top mine, comparing to several other methods, we also just briefly covered, like turbo topic, like TNG, like CURT. If you compare with others, the first interesting thing is it is quite efficient. Okay. You probably can see, if you compare with all the columns, okay, what you can see is top mine is very close to LDA. Okay. The reason is top mine actually is a sub-procedure, is phrase LDA. Okay. It simply says it takes something like LDA as one part. That's why, if you look at the phrase mining, even it's very efficient, but you have to think about it. You want to generate topics, you need to call phrase LDA. Okay. But why, if you even look at this, in many cases, this top mine could be even shorter, even faster than LDA. Anybody can explain this? because you take RDA almost like a sub-procedural call. Why? This one is shorter. Yes, Stephen?
You have fewer phrases or fewer grams.
Yeah, excellent. Yeah, this is exactly. You can see is you originally take every single word, every unigram as a unit. Okay, but now you take k-grams. You can think of it. You take phrases, quality phrases, as a unit. The quality phrases could be less. Number of quality phrases could be less than the single word. For example, support vector machine now is only one instead of 3 words. You count as one phrase, right? So in that sense, of course, some you still take single word as a part of it. So that's the reason you can see it is close, but it could be a little more efficient, right? So that's a very good reason. Thank you. Now, even you look at using z-score, you look at the changes. You can see if the z-score is somewhat higher, that means actually the quality is better because it's more coherent. Then you look at these several different methods. You can see the top mine is the highest one, the second one is curd, and turbo topic. Okay, that's on both ACL corpus and the 20 conference corpus. It shows the quality is better than the previous method. And if you look at number of correct answers by phrase intrusion testing. So what is phrase intrusion testing? The intrusion testing actually was done by a human. You can think it's sort of like you take a human judgment to be part of your argument. Okay. How the human you do the intrusion testing is you generate several topics. For example, this one is about Mexican food. This is about shopping. This is about, say, the European food. Okay. Suppose you look at these several things. You take, for example, the Japanese food. You throw it into Mexican food. That means you intentionally put this topic and throw it into the other topic. Okay. That's kind of intrusion because you take the Japanese food, you throw it into Mexican food. It's intrusion. Okay. If the user, the reader, can identify, so these are aliens. Okay, that simply says your phrase, your topic modeling generate very good topics. Every topic is so self-contained, so unique. Okay, you throw it into the other topics, people can detect it. That's the intrusion, people can find it. Okay. So if you see the number of correct answers, that means people can judge this one is intruder. This one is the intruder. They can take it out. And if people can judge the correct answer, simply says your topic model did a good job. Okay, you really put Mexican food into the Mexican one, the Japanese food into Japanese one. Okay, so in that sense, you can see top mine got the highest. Simply says, you generate good quality, human can judge, right? So that's intrusion testing. And this is a phrase quality z-score you probably can also see is better, right? So that means if you compare 3 strategies we just introduced, the first one is you generate a bag of words, then generate sequence of tokens. That means at the very beginning you get a bag of words like a bigram, n-gram, this kind of model. Then you try to generate tokens. Because your bigram or n-gram, the pairing is a little blind. You try to pair everything into bigram or n-gram. So it is pretty slow. And sometimes you get overfitting. Okay. The second strategy is you first do topic modeling. Then you, within the same topic, you try to combine them to get words. Okay. That's turbo topic. Curd, they do this. But this one is, if you, at the very beginning, you do topic model, a good phrase, you split them into different topics, you'll never be able to find them, right? That's what we said, knowledge discovery or support vector machine. Once you split them into different topics, you will never be able to recombine them into a good phrase. The third one is Ahmed, the top mine is using, you first do phrase mining using those simple statistics, just based on, whether they get together. It is, in principle, it's very rare. Now you see it is not rare. Okay, so this is a good phrase candidates. You use these and plus 4 different criteria, evaluating them. Then you finally put them into topic modeling. You generated really good ones. Okay, so that's for the topic or phrase mining. Okay, this one is another picture about the same fall. You can see the Iwasu is really, really broad. Okay, and those birds are also very big. You can see it's like eagles. Now we look at the last phrase mining method we generated called sec phrase. That's the one yesterday. These sec phrase 2 authors, Jalu and Jinpo, they actually reported to Yuri Laskovic on this phrase mining. Yuri got very impressed. I think this one is very useful. Remember, he is also working at Pinterest as a chief scientist. He found it's truly useful in industry. Okay, and this one not only get a Yelp Dataset Challenge 2015 grand prize, but also even like TripAdvisor contacted us, said they are using this. They want to extend it to multiple languages. Let's look at why this one is so interesting, generate the quality phrases, and also can be extended to multiple languages. Okay. Actually, top mine, I just mentioned that one, also can be extended into multiple languages. Why? Why it is language independent? Because you just look at the words, their frequency, their combination, right? Look at the words combination, it can be in any language. You don't have to be in English. That's why it generates quality phrases for English. You go to Spanish, you go to Chinese, they also generate very high quality phrases. Okay. So this method, this mining phrases, the first interesting thing, actually this one is also in top mine, is the traditional data-driven approach using frequent pattern mining. But the raw frequency is not very good. You have to do phraser segmentation. Actually, the phraser segmentation means you go back to see for this particular sentence, which one it counts, which one it contributes. I will give you a little example, but actually this one is also used in top mine. Okay. Then you probably can see, I give you the whole workflow like this. Okay. We get a raw corpus. Then you, based on frequent patterns, that means they frequent together, okay, you generate the candidates. You generate a lot of candidates. And for these candidates, you need to use some tricks like top mine using 4 standard, concordance, popularity, completeness, and distinctiveness, all these things putting together to judge. Okay. Actually, for sec phrase, the method is they add one more important thing is training, because the previous top phrase, they do not do any training. And this one says, if you give me a little training example, I can do far better because I can put this one into a classification process. Okay. So this is like a word cloud, like a data mining, data sets is more popular, so it looks bigger. Okay, it's printed bigger. Like text mining, like a web page, or data mining algorithm, not so popular, so it printed smaller. Okay, but no matter what, you want to get a true frequency, because those are the frequency you just count every possibility. The true frequency, you need to do the document segmentation process. What is segmentation? You probably can see like this. Suppose we found, here you found a heterogeneous information networks. Okay. Heterogeneous information networks is a phrase in this one, but information networks or heterogeneous information also could be candidate phrases, right? You can see, because any component, subcomponents like information networks is a perfect phrase. But why this one will only count to heterogeneous information networks, not information networks? The reason is you can see here, this one, you go back, you say heterogeneous information network has a high vote, and here it contains the full thing. Okay, so this phrase contribute to, this phrase in this document contributes to the count or frequency of heterogeneous information networks. Then it will not count to the subsets, because the subsets, is just because they want to generate this, they have to generate information networks, but they do not intentional to credit to information network. They intention to credit to the whole thing, to the whole phrase. Okay, that's the reason you will not find a lot of counts in this one. You don't find any count for heterogeneous information or information networks. It only contribute to the true count of heterogeneous information networks. Okay, so that's we call segmentation. Okay, that means which one really counts. You need to give a credit to the right one. Okay. For example, here you can see there's a linear dimensionality reduction. Of course, there's dimensionality reduction. There also could be linear dimensionality. Okay, but since you count to linear dimensionality reduction, you will not count to dimensionality. Okay, that's the segmentation process. Now we look at the whole, the whole flow chart. You can see is this. You get a corpus. Then the first thing is you do frequent pattern mining. Okay, you find something frequent together, likely will be the candidates. Okay, that means from large corpus, you first do frequent pattern mining. Then you get candidates. Then you do feature extraction. That means you extract some important possible phrases as features. Okay. Then these features can, based on the Fraser segmentation, Fraser segmentation simply say which one, you go back to the corpus, which one is the right phrase, you take them out. You take the right count out. Then you put into this feature space. That means you integrate the features and the segmented true count of the phrases. Okay. Then what you do is you put into a classifier. This one is new. It's different from TopMine. Okay. TopMine has no classification process. But you'll probably see, even if you attended yesterday's talk by Yuri Leskovic, you see a simple classification like decision tree can do a lot of good, right? It can even beat judges. So this one is what they did is in their experiments is they pick up 300 generated phrases, ask human to label it, whether it's good phrases or not a good one. For example, like you see the Mexican food. They may have something like a food was good. Then the human say, this is not a good phrase. You don't need to do parsing. Okay. You just say, this is not a good phrase. You just say 0, or you cross it. Say, this is no good. Okay. But if they say chips and salsa, you say, oh, this is good. You cross. You say, this is 1. You basically assign 1 and 0. Simply say 1 is a good phrase, 0 is not a good phrase. Okay. How many phrases human has to give hints? Okay. What they tried is they tried gigabytes. Every test they try gigabytes, those kind of the corpus. But they only give 300 label data. That means 300 is about, half of them say good phrases, the other half may say not so good phrase. Okay. So they use this training or labeling. Then they construct a classifier. And then they use this classifier to go back to estimate the phrase quality and then redo the segmentation. Because originally, you may say, like if you just give you a back example. For example, originally you say linear dimensionality reduction. Finally, you find actually linear dimensionality reduction not so good, but dimensionality reduction is good. Then you will recount it. You say, now I credit to dimensionality reduction, but not credit to linear dimensionality reduction. So in that case, you actually get the better counting. You eliminate some phrase like food was good, it's no good, you just eliminated it. Then maybe they have Mexican food, it's good. Then you say food was good, it's no good, but Mexican food, now you get a count, right? So once you do that, finally you will generate quality phrases, right? So that's the whole flow chart. They basically say this part, they call this one is classification of the phrase, or they say seg phrase. After you redo the phrasal segmentation, they call the whole process as seg phrase plus, because you enhance the quality. Yes. Yeah, the features are actually, the feature basically is you get a candidates, you get a corpus. Essentially is you do some segmentation, you get right counts. Those are good things you count as features. Okay, so essentially it's just phrases. Okay. So of course, the good question is the feature. When you judge them, you were thinking about these four, actually the same four criteria. One is popularity, like we already said. Another, concordance. That means they really getting together very frequently. So the concordance, informativeness, and completeness. Okay. So these four, it's the same as TopMind, same as Kurt. They use these four as the standard. Okay. So in their recognition, you probably can see this. Okay. I probably should, I think this part I maybe get a little cut off. I will go back and check this slides, okay? But what you can see is this. You first mine frequent k grams. Okay. K usually is a small one. For example, you can think about bigram is k is 2, trigram k is 3. In the experiments, we just use 6 as a k. That means we generate the maximum 6. But sometimes you may need adjustment a little. Just give you a simple example. If you mine the medical phrases, sometimes they get pretty long. It's more than 6. If you really go down there to mine the PubMed data, you probably want to enlarge this instead of k is 6. You may say, I can try k is 8, k is 9. You may get a much longer phrases because some medical terms, they get together, it can form a really big one. Okay, and but normally you mine like New York Times, 6 probably is good enough. You look at the United States of America or University of Illinois at Urbana-Champaign, probably that's 6, right? So that's good enough. Usually you rarely find even longer phrase. Okay. Then at the very beginning, your popularity is just a raw frequency. But you have to go back and adjust it, okay? So what we did the adjustment is this, okay? Suppose you get, say, support vector machine, you get this paper demonstrates, okay? You probably see how do you combine them to form phrase is you will think about it. Support vector could be a left-hand part, left part. Machine could be right part. What you want to see is these two things getting together, the chance, whether it's high, it's low. You can use significant score. But here, actually we can use point-wise mutual information, or we can use point-wise K-R divergence. I will give you a little introduction on this. I hope, if you took CS412, You probably should know what is mutual information, what is scalar divergence. But anyway, let's just give you a little introduction on these pointwise mutual information. Okay, you can see is you have probability of both support vector machine getting together is a P, it's a phrase. This is a whole V. Okay, but this one you want to see is the left part. What's a probability? That means what's the frequency, relative frequency of the left part. That means the support vector machine within, for support vector machine, support vector is the left part, machine is the right part, right? So you will look at the probability of support vector, you will look at the probability of machine, then you look at the probability of support vector machine as a whole. Okay. You count all these. Then the PMI simply says, if this one happens much higher than expected, these two are like expected. You think about if this one is 1 over 1,000, this is 1 over 1,000, you get together, it should be 1 over 1,000,000, right? But now you got a chance is much higher. It simply says this one is much higher than 1 over 1,000,000, okay? Then that means this PMI is higher. Higher means they should be a phrase. They should be a good phrase because their appearance together is much higher than the pure independent occurrence of those probability. Okay, so that's why you get PMI. Of course, you don't want to make it too big. That's why you take the log. Okay, you take log, but they are still higher. Okay, then you get a higher PMI. It simply says the mutual information is high, it's likely to be a good phrase. Okay. Similarly, you can use scalar divergence, which actually, if you look at this formula, is similar, except they time this P, this probability at the outside. Okay, that simply says if this one's probability is higher, then this pointwise mutual information, you time this together, it could be even higher. Right, so that's just another measure for this. Those are different measures, but you know is the higher the chance to get together is higher. Okay, so that's the same thing like here. You see this paper demonstrates if you have lots of such things, then this could be a candidate phrase. Okay, but if this is not the whole story, because otherwise you will say support vector machine is a good phrase. This paper demonstrates it's also a good phrase. Okay, in this test, it is a case. Okay. But once you go inside, you still have to use classification. You may say, oh, based on my classification or other training methods, I found this paper demonstrated is nothing. Okay, I will remove it. That phrase, okay, you probably can see when you try to derive informative, another trick they used is if this stop words is right at the end or the very beginning. Okay, that means if you start with a stop word, or ending with a stop word, you will think this stop word should be removed. Okay, that means you say something is machine learning, or machine learning is. Or you say of machine learning or something. The stop words right beginning or at the end, so unlikely it should be part of the phrase. That's why you get machine learning. But if you say University of Illinois, this of is in the middle. Okay, so that middle is still useful. So you will still have University of Illinois as a phrase. Okay, but if you say University of, there is no Illinois, then of something else, you probably could cut this off. It's university itself become a phrase, right? So that's the trick. But I think everybody can work this out. If you really do experiments, you will find these rules. Okay, and there are some other things like IDF. IDF is in IR. You probably know we use term frequency and inverted document frequency. So it's TF and IDF. Okay, This IDF, just inverted document frequency. Then you can use average inverted document frequency over the words to measure the semantics. Simply says whether, in the documents, whether it's in this document, if it's only frequent in one document, not frequent in many documents, you probably will count it a little less. But it's frequent in many documents, okay, so to that extent, it could be more important, right? But if it's frequent in every document, it becomes stop words or stop phrases. You probably do not want to count it as well, okay? So you probably can see, sometimes you may even see that state of the art. They have a dash around. But dash, in your calculation, quotes, brackets, or dashes, you're probably thinking the probability getting together is even higher. So you take a state of the art to be a phrase is even higher than you just break them apart, say state of the art. Okay, so they use those heuristics, try to glue them together. Of course, you can use more NLP technique. For example, you can use POS tagging. POS means part of a speech. You can tag this. It's a verb, or it's a phrase, it's a preposition. If you do this, you can get even better ways to do it. Okay. I actually just did a PhD course. I gave the students. I do not know anybody took the course. Somebody took it, right? So I ask people to say, what is the additional NLP technique you can help? Okay, you probably see here, we didn't put it to POS tagging. We put it to chunking. We put it semantic parsing. Okay, those are the NLP technique you can use it to further enhance the phrase mining, right? Of course, you can put more, but these things, I put it down here, simply says you definitely can use it, okay? Of course, some students said maybe I forgot to put something, but as long as you put something reasonable, okay, usually you get good credit, okay? So you probably can see for the classification, you can say, like a support vector machine, you say this one's good. You give a 1. You can say the experimenter shows it doesn't look like a phrase. The person, the human can give a 0. You get a gigabytes corpus. You only need 300 such labels. You actually will help the whole learning process. Okay, then the finally generated will be really good. Okay. And the method for the classification, yesterday, Yuri said he just uses, simple decision tree. But decision tree he uses is pretty deep. I remember yesterday he said it's about, the length is about 20. Okay, the 20 is pretty deep. Okay. Here, for this one, we did not use that deep tree. We actually use random forest. Random forest has additional nice feature comparing with decision tree. Actually, yesterday, if anybody read this, you probably want to ask Yuri why you don't use random forest using decision trees, which is a good question. Okay. Actually, random forest has some nice features because you generate, you can generate one tree full of one tree. Actually, one tree sometimes could be a little too biased. But if you generate, in parallel, generate multiple trees, okay, you sort of doing ensemble. You just put those trees together. You do a vote or something. In many cases, you will get an even better model. Okay, so that's the reason we actually use random forest as a classifier and use a little bootstrapping method. If usually if you have only limited labels, you need to use bootstrapping to enhance your ensemble, your random forest. Okay, so those are the typical classification tricks which are very popularly used in machine learning, right? So then you look at the Fraser segmentation, how we did it. Okay, you can see you have this typical things in the text. You say a standard feature vector machine learning setup is used to describe something. So you probably can see feature vector you can get as as one phrase. Machine learning, you get another phrase. But remember, actually in the middle, you may see there's a one called vector machine or feature vector machine. Okay. Is a vector machine should count as a support vector machine, that one? Actually, here you probably see, if you find a good candidates already, you find feature vector is a good phrase. Machine learning is a good phrase. You will not count this vector machine together, because even vector machine is frequent. But in this particular sentence, okay, the vector machine actually will be erased by feature vector and machine learning, because these are very good phrases. Both are good phrases, right? Then the middle, like a feature vector machine or vector machine, will not be a phrase. Okay. So that's the case. You do phrasal segmentation, you will get a true frequency. We call this one as a rectified frequency, instead of you get a raw frequency. Simply says, suppose this one is a fictional example. Okay, you probably can see is, suppose you plow through your corpus. You find your support vector machine appear 100 times, support vector appear 160 times, vector machine appear 150 times. But if you really go back to your document, look at every sentence, say which one it should belong to. Okay, so you probably can see the support vector machine, they get together. Actually, once you rectify it, you will say this one actually got probably really 80 counts really belong to an independent phrase, support vector machine. But a vector machine, you go down there, you find the vector machine is not a really good one, because most vector machine only contribute to the phrase support vector machine. They independently occur very rare. You can see here, independent only occurs 6 times. Okay. In that case, you will say, yeah, support vector machine is a good phrase. Support vector is also a good phrase because it independently occur 50 times. But vector machine is not a good phrase because independently they occur very rare. Is that clear? Okay. That means you just cannot blindly just do the blind counting. You say, oh, which one is frequent? You have to go back to the document and say which one it really belongs to, right? So that's a very, very useful one. Okay. Now, with this whole process, okay, you actually do you give the quality score to the real phrase. You actually use the whole classification process. In the sec phrase, they also introduce a little on length penalty. Remember, we originally said a longer one, like support vector machine, is a good phrase. Okay, but sometimes you get a too long one. Okay, sometimes they happen together, get too long one. They may not be a very good phrase. Actually, subcomponents may be a better one. So, simply says they introduce a length penalty. When the length too long, then you probably give a little preference to the shorter phrase. Then you'll be able to find a shorter phrase rather than find an extremely long phrase. Of course, this is just based on experiments. For different languages, you may use different things. Okay. So I think that's the whole trick. You can see the whole process is you use a feedback. You do the classification, you go back to do the phrasal segmentation. Okay, this is the sec phrase. But you take this phrase segmentation result, you redo the classification again, then you do the phrasal segmentation again. You can further improve it. Okay, so that process is called sec phrase class. So for sec phrase plus, they do the iteration. That means they do classification twice. Okay, so sec phrase only do it once. Now you probably see the differences. Okay, top 9 do classification 0 times. Okay, because they don't really have training set. They did 0 times. They just generate the phrase. Okay, But sec phrase, they do classification once. Okay. Then sec phrase, they do classification twice. Okay, you probably can see. That's based on experiments. They clearly see after phrasal segmentation, you do classification again, you improve the accuracy, the better, the quality. Then you may say, what about I do it many, many times, whether it improves? Okay. Actually, based on their experiments, because they only use 300 labels. Okay. If you do the classification again and again, actually you get overfitting. Then the problem is you even lower down the quality. Okay. But it's very interesting is during the PhD preliminary exam, okay, one professor raised a question, said because you use 300 labels, which is very small compared to the gigabytes, okay. But if you do not use these 300 labels, but you take the whole Wikipedia, like Wikipedia has a title has lots of good phrases, right? You go to Wikipedia, you say support vector machine, you will be able to find it. You say linear, classifier, or like many things like probability graphic model. You go inside, you can find it. Support vector. What I mean is, Wikipedia give you many more good phrases instead of 300. It probably give you about 1 million, right? Give you those many good phrases. You take those good phrases because it's already labeled, right? Every entry in Wikipedia you can think it's a labeled one by human. Okay. You put this one back. Whether you do multiple rounds, it will help. Actually, it's likely. We haven't tried it, but it's a very good suggestion. Simply says you do not use 300 labels, but you take the whole Wikipedia as your label, okay, positive label. Then likely you may need more rounds. You can further improve the quality of your sec phrase. Okay, that means you may get a double or triple plus. This is only do it once. But there are many ways to implement. You may try it actually because this whole thing is open source. Okay, you take a Wikipedia, you can try it again and again to see how it happens. I think it will improve. Obviously, you get 300 label, you get overfitting, you get 3 million label. It may help you more, right? So that's the story about sec phrase. The performance is you need to compare with a lot of rivals. What they did is they first do compare with chunking method because the chunking has been used in NLP. The chunking, what they did is this, okay. The chunking is they actually take all these candidate things in, then they say where it starts, where it ends. They use lots of training, lots of labeling. They take this doing the chunking, okay. But I'm not going to get in the detail on the entity name chunking, okay. That's an NLP method. Another is unsupervised raw frequency-based method. For example, one is done by Aditya. Aditya now is a professor. When he did this, he was a PhD student in Stanford. He published his paper in VLDB 2010, and we did compare with Aditya's work. Okay. Then we compare with Arkishki's method, TopMine. Okay, those are actually it happens, these two both are in the UIUC now, right? And we also compare with supervised method like Ian Witten, who wrote a very good book, and that's called Key. Okay. So the data sets we use is very big. You can see DBRP is 2.77 million documents. YERP is 4.75 million documents. Okay, there are lots of million of words, but label is constantly only gives 300 labels. Okay, even you get millions of them. Okay. Then what we use actually is every time you want to judge whether it's good or not, you take a Wikipedia as a standard. You generate one, you say, oh, Wikipedia said this is a good phrase. Then you generate the same thing as Wikipedia, you probably get it really good. We take a Wikipedia as a golden standard to check. Okay. So now you can see the method, different kinds of methods, their comparison on the quality. This quality is based on precision recall curve. And you can see this one is on academic data sets. It means DBRP. Okay, this is using wiki phrases. This is using pooling method. The top one, the black one, is on the top. The top one is sec phrase plus. You can see the top one. Then you see all the different things. This contra expression, you only get a one cross point because it is too expensive to run it. You can see that's a one done by Aditya, but that's a database method. They try to exhaustively find out many things. That's Aditya's PhD student. He did one interesting paper. But you can see the quality of phrases, the sec phrase is the highest. Okay, and this. Then you look at top mine. Top mine is lower. Okay, but probably you will say it is not very fair to compare this because top mine does not use any label. Okay, this one does use label. Yes. Okay, yeah. The question is which one which one is a precision, which one is a recall. Actually, I think this is the final one, like this one, is based on my memory is F1. Okay, the F1 means the harmonic mean of precision recall. Even the Rodin's precision recall curve actually is sort of like an F1 value instead of precision average with recall. It's a harmonic mean. Okay, so it's a very good question. Because most people actually compare this using something like F1, right? And this one is about scalability. That means you keep adding more and more data sets. How slow or how fast, how much time you will need. You can see, like the academia data. The academic data get 600 megabytes. But Wikipedia get 20 gigabytes. Okay, then you can see the time running actually is pretty reasonable. Like all these is less than 1 hour. Okay, but of course you get a Wikipedia that size, you have to use 28 hours to process it. Okay, but the best thing is you look at the example to see what is the quality you can reach instead of just look at the precision recall curves. You can see is the left-hand side is sec phrase. The right side is chunking using TF, IDF, and C value to judge. These are the ranked one. That means the top one is the most highly ranked phrases. What you can see here is this one is from Sigma, which is a database conference. The red one is those things only appear in sec phrase plus. The blue one are those only appear in chunking. So you just based on the people's, human, you probably can judge the quality. Because you can see this one is relational data, join query, high dimensional data, two-phase locking. Anybody in database course, you probably see those two-phase locking or relational query. Join query is a very popular phrase, right? You don't have this, you don't really have a database course. But here you can see they found large volume, efficient implementation, large collection, important issues. Those actually not necessary to be in a database. It could be anything, right? Even you go to any computer science, they have efficient implementation, large collection. So it's not really that sharp. Same thing, you go to KDD, the data mining conference. You probably see those red ones, so time series, gene expression data, frequent subgraph, categorical attributes. If you do data mining, you know these are very, very important phrases. But you go down here, like you look at name chunking, what they generate is important problem, effective way, small sets. Those actually can happen anywhere. Right? A very interesting thing is even you can do a little a little embedding. That means you use a little embedding method You take any phrase like data mining. You can use these two methods to do a little embedding to see what kind of surrounding phrases you can generate. Just give you a simple example. You take a Blu-ray. Okay, the Blu-ray, you probably can see the sec phrase will generate DVD, VHS, CD, new release, Sony, those things. Okay, these actually somehow very much relate to Blu-ray. But if you look at the name chunking, you do the embedding, you get a new microwave, lifetime warranty, recliner battery, or new battery. Obviously, it's too far away from Blu-ray, right? Then the same thing as noodle, you probably see. You get noodle, you will find a ramen, noodle soup, rice noodle, egg noodle, pasta. This is a sort of a noodle-like, right? But the other one actually give you something like a stir fry or something. That's not really good things like a noodle. Okay, of course, the stir fry does happen with something with noodle, but it's not really noodle like fish balls stir fry. Right? So you probably can easily see using Yelp. You also get the quality phrase will generate meaningful results. Okay, so we finish this. This one actually is using. If you see, this is from English gigawords. We do the phrase mining. It generates lots of things. Actually, if people say if you know the historical names or a lot of names, you look at those names. They make a lot of sense. You generate phrase. Name actually are the phrases as well. You probably can see it's pretty interesting. And some people try the Spanish or try other things. We did try multiple languages. The reason actually is because you use all the features is somehow language independent. Okay, so this one is Chinese. Okay. You can generate the Chinese phrases, which is very hard because Chinese has, between the words, any phrase, they don't have space. The whole sentence, all the things, there's no single space for the very long sentence. So it's very hard to get a phrase, but still get a very good phrase. This is Arabic. I could not read Arabic. This is what, Ahmed can judge, said this is the English translation, also is a very good phrase. Actually, currently, this group, okay, I mean, Jingbo and Jialu, they are working on the similar as what TripAdvisor asked. They're working on 10 different languages. Okay, some they do not even know, like French, German, Russian, Korean, Japanese, all these things. And they try to generate all the good phrases. They actually told me they made a very good progress. What they want is a crowdsourcing. Simply says they want people to know Russian or know Japanese to judge whether these are good phrases. They want to put it into the crowd to let people judge whether it's good phrase or not good phrase. But it's complete blind because they use the same software, generate all the different phrases for different languages, which is, for most people, it's very surprising. Okay, but they rely on big corpus they generated. So now I will pass it to Ke Yang. He's going to give a little introduction on the topic modeling, which I think is also very, very useful and important. Okay, I do not know whether you want to do it in the mode of, let me see whether I can get the right mode. I think this is yours, right? Which one is? Let's get the time.
Probably just use that one.
Let me see whether I can get. Let me see. We just go back to this one?
Yeah.
Okay. Yeah. Okay, I'll pass it to you. Yes? You have any question? Yeah, we can discuss a little more. Okay. You reserve the question for the next lecture. Okay. Thank you.
Good morning, everyone. During last lecture, also this lecture, we learned Top1, which is a state-of-the-art work that combines phrase mining and topic modeling. So today I would like to go a little earlier to say one of the earliest work in topic modeling, which is this probabilistic latent semantic analysis, or PLSA. to serve as a basic introduction to probabilistic topic modeling. So first, let's ask ourselves a question: why I want to do topic modeling? Or let's first think about what is a topic. I think the meaning of topic could be pretty intuitive to everybody, but it's roughly the main idea discussed in text data, and it reflects the theme or subject of a discussion or conversation. The topics can have very different granularities. The reason we want to do topic modeling is that many applications actually require the discovery of topics in text. For example, we may ask the following questions. What are Twitter users talking about today? Or what are the current research topics in data mining, and how are they different from those 5 years ago, and so on and so on. All of these questions require the discovery of topics in text, and all of them can be solved using topic modeling. So the tasks of topic modeling are twofold. The first task is to discover the key topic from our text data, and the second task is to figure out which documents cover which topics to what extent. And here, in order to instantiate or substantiate this task of discovering key topics, the first challenge faces us is how do we represent the topic. So the idea that the PLSA proposed is to use a word distribution to characterize a topic. For example, we can say this distribution, this topic is probably about sports, and also this blue one is probably about travel, and so on. And here, a word can appear in multiple topics. For example, this travel, but with different probabilities. So with this idea of representing a topic by a word distribution, we can then give the formal definition of probabilistic topic modeling. So the input is a collection of text documents and a vocabulary set, and also the number of documents k. The outputs, as we've seen before, are twofold. The first part is the k topics, and each of which is a word distribution. And the second part is just the coverage of topics in each document, denoted by this pi. So pi ij means the probability of document I covering topic theta j. So this is an example output of our algorithm. So we should be able to learn the word distributions as topics, and also learn which topics are covered in which documents to what extent. So now our task becomes clear. Our task is to estimate those parameters as accurate as we can. And the PLSA actually approached this problem by using a generative model. It means that we want to model the generation process of our text data, which is controlled or influenced by our parameter. So we want to sort of adjust our parameters so that the likelihood of observing this text data is maximized. So in the following, let's use a simplified case to illustrate the basic idea of PLSA. Actually, the core idea of the real case and the simplified case is really very similar. So in the simplified case, we only have two models here. One of them is theta b, denoting the background model, and the other one is the theta d, denoting our topic model. So the words with high probabilities in this background model are those common words that could appear in any text corpus. And the motivation for us to use such a background model is exactly to factor out those common words to better detect our topic, which is probably about text mining, as you can see. So here, the generation process is like we first assume every word in this document is generated independently from each other. Then how do we generate a word? There are two steps. In the first step, we randomly choose a model based on this prior probabilities among all the models. And then within a model, we, based on the word distribution, randomly choose a word. So here, the prior probability serves the role as the previous pi's, which reflects how important a model is to a specific document. And here, we assume we only have one document. So recall that our task is to adjust those parameters so as to maximize the probability we observe our text data. And here, the only unknown parameters are these parameters in our topic model. If you think it for a while, you'll find that it's actually not that easy to directly estimate those parameters from this data, because we do not really know which words are generated from which model, and that's actually a general challenge faced by a mixture model like this. So why not further simplify this scenario? So what if we know which words are generated from which model? What if we know this partition? So suppose we know all the black words are generated from the background model and all the blue words are generated from the topic model, then it will be extremely easy for us to estimate those parameters. We can just use this frequency ratio or normalized frequency as our estimate. Unfortunately, we do not really have this partition. So let's consider another question. What if we have all this word distribution? In that case, could we estimate the partition itself? So actually, we can just by using the Bayes rule. So here, following the generation process of our model of the data, we can just multiply the prior probability and the likelihood of observing a word given a topic and normalize them using the Bayes rule to get the posterior probabilities of observing a given word, the probability of a given word belonging to a certain topic. So if we combine these two, we'll find that if we know the word distribution, it will be easy for us to get the partition. And if we know the partition, it will be easy for us to get the word distribution. So it seems that we are facing sort of the chicken or the egg dilemma. But actually, we have an algorithm that's sort of specifically designed for this dilemma. So that's our EM algorithm. So the idea of EM algorithm is that these two subtasks of partitioning the data and estimating the word distribution can mutually enhance each other, in that a better estimation of the word distribution can give us a more reliable partition, and a better partition can give us a more reliable estimate of word distribution. So the EM algorithm just iterates over these two steps and improve the estimate. So here, the formula of each step is just the one we see here. It's just the Bayes rule to get the posterior probability. And here, the M step is very similar to the frequency ratio we see here. The only difference is that we do not really hard partition every word to say it's 100% from a model. Instead, we use this soft partition to say to get the softly allocated counts of every word belonging to a model. So here's a simple realization of EM algorithm. Let's suppose we can pack all of our parameters in one dimension. This very non-convex function is our original likelihood function, and it cannot be directly optimized because we have latent variables here. So the way EM algorithm approach this problem is first use this E step to compute a lower bound like this, and then use M step to maximize this lower bound. And it turns out that the lower bound constructed by the E step is guaranteed to be tight with our original likelihood function as our current guess. So this good property actually guarantees we only improves after each iteration in terms of likelihood. So we will finally converge to a local optimum. So finally, let's take a quick look at the real case of a PLSA. So here we still have our background model, and we still have a probability controlling whether to choose the background model or not. But instead of one topic, here we have k topics. And another difference is that here the prior probabilities or the coverage probabilities among different topics are document specific. So here we have multiple documents. So each document will have its own pies to control the prior probability or coverage probability among different topics. So here's totally k+1 way to generate a word. For example, we can first choose not to use the background model, and then based on this coverage probability, we choose a specific topic, and then from this topic, we choose a specific word. So this is the formula for the real case of PRSA, and this is E step. Don't be scared by the formulas. It's really the same as the previous case. It's just longer. So here, the second formula measures the probability that a word in document D is generated from the background model. And the first formula measures the probability this word is generated from a topic model theta j, given that we know it's not generated from the background model. And very similar to before, we still use Bayes rule to estimate estimate these probabilities. So this pi is just our prior probability, and this term is just our likelihood. So we just normalize that to get the posterior probability. And this is the M step. So here, as we can see, this part is exactly the same for these two formulas. It just mirrors the softly allocated word counts to topic theta j. And here, in order to mirror our coverage probability, we want to know how important this topic is to this document. So we want to marginalize over all the words to get the overall importance of this topic to this document, normalized over all the possible topics. And here, the second one, we want to get the word distribution. So here, we want to know how important a specific word is to our topic. So here, we want to marginalize over all the possible documents to get the overall importance of a word for a topic, marginalized over every possible words in our vocabulary. Finally, I want to say a little bit about LDA. So PLSA is one of the earliest work in topic modeling. It has been extended in many ways, and one of the most successful extensions is LDA, latent dirichlet allocation. So the main limitation of PLSA is that despite using a generative model, it is not fully generative because after learning the K topics from our data, we can only deal with the documents appearing in our corpus. We cannot deal with the documents that is not in our corpus. That's because these pies. So these pies are document-specific priors. So they are learned from our data. And for new documents, we actually do not have these pies. So that's make the model not fully generative. And actually, LDA overcome this limitation by a very smart idea. Unfortunately, we won't have time to cover that, but you are definitely recommended to read that LDA paper to check the smart idea. So I guess that's it. Thank you.
Yeah, I think this is a very good introduction. So you probably want to read the slides. The slides you can get. I just tell you how to get the slides. Okay, you go to the course page. There's one said this link said CS512 2016. If you click it, our class presentation are there. So you can download any slides, you can read it. Okay, thank you. It's very good.